So today is 12:12, and our outcome, I can represent a balanced redox reaction equation using half reactions. So we're going to work on topic 4.9 today. For your drill, I'd like you just to take a couple of minutes to discuss 4.8 reflection questions with some peers. So take a couple of minutes and do that. You can pause this video and then return here when you're ready to continue. So our outcome, we want to represent these balanced redox reactions using half reactions. So redox reactions are a really important class of reactions. A good example would be the formation of sodium chloride from the reaction of sodium metal and chlorine gas. So in this reaction, the sodium loses an electron while the chlorine atoms are going to gain electrons. So this gives us Na plus and Cl minus ions. So reactions like this, where one or more electrons are transferred, is called an oxidation-reduction reaction or a redox reaction. So there's lots of examples of this reaction. Photosynthesis in plants, the reactions that we use for energy production, such as the combustion of methane as shown below, the oxidation of sugars, fats, and proteins in the human body. These are all redox reactions. Combustion reactions, which provide most of the energy to power our civilization, also involve oxidation and reduction. Now, in my previous example, it was really easy to see why electrons were being transferred. You end up with Na plus and Cl minus. But here, it's not quite so obvious. So even though none of these reactants or products are ionic, the reaction still involves a transfer of electrons from carbon to oxygen. So in order to explain this, we need to introduce the concept of oxidation states. So oxidation states are essentially just a method to keep track of electrons in redox reactions, especially when we have covalent substances involved. So remember that in covalent bonds that electrons are shared. The oxidation states of such atoms are determined by assigning electrons to atoms. So for a covalent bond between two atoms, the electrons are split equally. If the two atoms are not identical, the shared electrons are assigned to the atom that has a stronger attraction for electrons. So this is all summed up with these rules here. So the oxidation state of an atom in its elemental form is 0. So for example, sodium in its elemental form is a solid. So if you have sodium metal, its oxidation state is 0. Something like oxygen gas, ozone gas, liquid mercury, anything that is in its normal elemental form, in its normal state of matter, is going to have an oxidation state of 0. For your monatomic ions, the oxidation state is the same as the charge. So Na plus has an oxidation state of +1, and Cl minus has an oxidation state of -1. Fluorine is going to be -1 in its compound. So for example, in HF or PF3, fluorine is going to be -1. Now, oxygen is pretty much always going to be -2 in its compounds. Now, there is one exception. If you have peroxides, so this is something that contains O2 with a -2 charge, like hydrogen peroxide, in that case, oxygen is going to be -1. So usually -2, but whenever we have peroxides, it's going to be -1. And hydrogen is going to be +1 in its covalent compounds. So H2O, HCl, NH3, hydrogen is going to be +1 here. Now remember that the sum of oxidation states is going to be 0 for a neutral compound. So for example, looking at my water example, hydrogen is +1 and there's 2 of them, and oxygen is -2. So that always is going to add up to 0. When you have a charge, like an ion, the sum of the oxidation state must equal the charge on the ion. So let's go ahead and take a look at a couple examples. So here we have a couple of chemical reactions where we want to identify the oxidation state of each element. So looking at the first one, I have Na solid. Since that's an element in its standard state, its oxidation state is 0. Same thing for Cl2 gas. That's the normal state of matter, the normal condition for Cl2 to be in. Now we have NaCl. So in this compound, Na has a charge of +1. So its oxidation state is also +1. Cl- has an oxidation state equal to its charge of -1. So here we can see that my oxidation states are changing. Sodium started with an oxidation state of 0 and it ended with an oxidation state of +1. Chlorine changed from an oxidation state of 0 to an oxidation state of -1. So let's go ahead and take a look at the next equation here. So this is the combustion of methane, CH4. So we have a rule for H, and the rule for H is that it's +1. Now in this compound there are 4 H's, which means my total positive charge is going to be +4. So in order for this compound to be neutral, the oxidation state on Cl has to be -4. Next we have this O2. So this is oxygen in its standard state, so its oxidation state is going to be 0. We have CO2. So here we have oxygen, which is always going to be -2, and there's 2 of them. So that's -4 for my negative charge. So my positive charge for carbon has to be +4. Next up we have H2O, which is again a neutral compound. So oxygen is -2 and hydrogen is +1. So that adds up to 0 whenever we account for 2 hydrogens. So go ahead and pause this video and take a few minutes to work through questions C and D. You can return here whenever you're ready to move on. So in C, we have PbS. So S is going to be -2. It is a monatomic ion. So that means the lead oxidation state must be +2. My O2 gas is going to be 0 because it's in its standard state. And then we have PbO. So oxygen is going to be -2, which means that lead has to be +2. And then for SO2, we have -2 for my oxygen. There's 2 of them, which makes -4. So my positive charge for sulfur has to be +4. For my last one here, I have lead oxide. Oxide is going to be -2 because it's a monatomic ion. So lead is going to have to be +2. For CO, O is -2, so C has to be +2. For solid lead, lead is a solid in its standard state, lead metal, so its oxidation state is 0. For CO2, we have -2. There's 2 oxygens total, so that gives me -4. So carbon must be +4. So redox reactions involve the transfer of electrons. So oxidation is the loss of electrons. So one of the things you can remember is Leo goes Ger. So Leo means lose electrons oxidation, and Ger means gain electrons reduction. So Leo goes Ger. That will help you remember what oxidation and reduction mean. Now in a redox reaction, both oxidation and reduction occur simultaneously. So this means that the reaction can be split into 2 half reactions. So the oxidation half reaction shows the species that is losing electrons, and the reduction half reaction shows the species that is gaining electrons. So that might seem a little bit confusing that reduction means gaining electrons. When we say oxidation, we're saying that the oxidation state increases. And when we say reduction, we're saying that the oxidation state reduces or decreases. So these were our answers from question 1. We want to write the half reactions, including which one is oxidation and which one is reduction. So take a look at Na. Na goes from 0 to +1. So this is going to be an oxidation. Cl goes from 0 to -1. So this is going to be my reduction. So I'm going to write this as two half reactions. So I have my 2Na solid becoming 2Na plus. And I have my Cl2 gas forming my Cl minus. And we're still balanced here in terms of atoms. So for my next one, we want to identify my two half reactions here. So we want to look for oxidation states that are changing. So first, we see that carbon is going from -4 all the way to +4. So that's going to be my oxidation. And we also see that oxygen goes from 0 to -2. So that's going to be my reduction. The oxidation state of the hydrogen doesn't change. It's still +1 before and after the reaction arrow. So I'm going to go ahead and split this up into my two half reactions. I have CH4 gas becoming CO2 gas. And I have my 2O2 gas becoming 2H2O. So we've split this into our half reactions. So we have our oxidation, that's going to be the methane to carbon dioxide, and oxygen to water is going to be my reduction. So go ahead and pause this video and work through C and D, and then return here whenever you're ready to check your work. So in question C, we have oxygen going from 0 to -2. And we have sulfur going from, let me back up here a bit. Sulfur is going from -2 to +4. So that's going to be my oxidation. Oxygen is going from 0 to -2. So that's going to be my reduction. So my oxidation reaction is going to be my 2PbS solid forming the 2SO2 gas. So there's my oxidation. My reduction is going from 3O2 to 2PbO solid. So this is going to be my reduction. Okay, last one here. So looking at my reaction, lead is going from +2 to 0. So that's my reduction. And carbon is going from +2 to +4. So that's my oxidation. So my reduction reaction is PbO solid to PbS solid. And my oxidation is CO gas to CO2 gas. So now that we're able to identify oxidation states and we're able to identify our half reactions, we want to be able to balance redox reactions. Now, since redox reactions involve the transfer of electrons, we have to make sure that the reaction is not only atom balance, we have the same number of atoms on each side, but we also have the same number of electrons being transferred on each side. So this is most easily accomplished through the half reaction method. So here we have some steps to balance a redox reaction. I know this seems like a lot of steps, but after you do this a few times and you kind of get the hang of it, it's not too bad. So first you're going to identify those oxidation states and split your reaction into its two half reactions. Then you're going to want to balance anything other than oxygen and hydrogen. Next, you balance oxygen by adding the appropriate number of water molecules to the opposite side of the equation. Then you're going to balance hydrogen atoms, including those that you added in step 2 as water, by adding H plus ions to the opposite side of the equation. Next, you're going to add up all of those charges, and you're going to make them equal by adding enough electrons to the more positive side. Now, as a rule of thumb, the electrons that you add and the H plus that you add are almost always on the same side. Now, the electrons on each side must be made equal. If they are not equal, we're going to multiply by appropriate integers, the lowest common multiple, so that the electrons are the same for each half reaction. The half equations are then added together, canceling out the electrons to form one balanced equation. Common terms that appear on both sides of the arrow should also be canceled out. Now, if this reaction is occurring in basic conditions, you have one more step. And in basic conditions, any H plus ions would be neutralized to make water. So to account for this, you're going to add hydroxide ions to each side to balance out the H plus ions and form water. And then once again, cancel out any common terms. In this case, you're going to cancel out water molecules. So let's do an example here. So we're going to take this reaction and we're going to balance this in both acidic and in neutral basic conditions. Now, in acidic and neutral conditions, we're just going to balance like normal. But in basic conditions, we're going to have that one more step where we neutralize any H plus with OH minus. So taking a look at this problem, oxygen's oxidation state is going to be -2. Now notice that there are 7 oxygens, so that's given me -14. And also notice that the charge overall is -2. So that means that the positive charge has to be +12, so you end up with that -2 charge. And there's 2 chromiums. So this means that the oxidation state on each chromium is going to be +6. For HNO2, O is going to be -2, and hydrogen is going to be +1. Now notice that this is a neutral compound. So the 2 O's are going to give me -4. The hydrogen is +1. So that means the nitrogen must be +3 so that this compound comes out as neutral. Next up, we have Cr3+. So this is just a monatomic ion, so the charge is the same as the oxidation state. Then we have nitrate, NO3-. So oxygen is -2, and there's 3 of them. So that gives me -6. But my overall charge is -1. So nitrogen must be +5 in order to give us -1 overall. So now we can figure out what's being oxidized and what's being reduced. So Cr is going from +6 to +3. So that's a reduction. And nitrogen is going from +3 to +5. So that's going to be an oxidation. So I'm going to go ahead and just write my half reactions. And I'm going to start with my reduction reaction here. So the first thing I want to do is balance things other than oxygen. So that means I need to put a 2 in front of this Cr +3, so I have 2 on each side. Next, I'm going to balance out the 7 O's. And I'm going to do that by adding 7 H2O's. So now the number of O's on both sides of the arrow is 7, but I also have just added 14 H pluses. So I'm going to balance that out by adding 14 H pluses on the opposite side. So I'm getting that 14 from 7 times 2 here. Now I want to figure out what the total charge is on each side of the arrow. So these 14 H pluses are going to give me +14. And this one, Cr2O7-2, is going to give me -2, which means that my charge is +12. On the other side, I've got a total of plus 6. So each of these 2 chromiums is plus 3, so that's going to give me plus 6, and water is neutral. So my total charge on this side is plus 6. Now we want to make these 2 numbers the same. So I'm going to add my electrons to the side with the plus 12 here. And in order to make this plus 12 into a plus 6, I would need to add 6 electrons. So now we're finished with our reduction reaction, and now we want to turn our attention to our oxidation reaction. So here's my oxidation reaction that we've identified. So my first step is to balance things other than hydrogen and oxygen, which means nitrogen in this reaction, and I have 1 nitrogen on each side, so that's already set. Now for my number of oxygens, I have 3 here and only 2 here, which means I'm going to need to add a water on this side. Now that my number of oxygens is correct, I need to balance the number of H's. So notice that there's 2 here and 1 here. So I need to add a total of 3 H+. So now we're atom balanced. Now we need to become electron balanced. So on this side of the reaction, my charge is 0 because both of those species are neutral. On this side, I've got -1 from nitrate and +3 from hydrogen. So when you combine the -1 and the +3, you end up with +2. So I want to make the charge the same on both sides. So this side has a +2. So if I add 2 electrons, that will become a 0. And now we're also electron balanced. But notice how in my redox reaction, 6 electrons are consumed, but in my oxidation reaction, only 2 electrons are produced. So those electrons that are produced during oxidation are going to be used in the reduction reaction. Now, right now, 6 is not the same as 2. So this means that my oxidation reaction happens 3 times for every 1 time the reduction reaction occurs. So to make that 6 electrons and 6 electrons for both reactions, I'm going to triple my oxidation reaction on bottom here. So this is where we end up. I've distributed that 3 across all of my bottom reaction there. So I took that 3 and just distributed it to everything. And that's how I end up with this reaction. So now we're almost done. We just need to combine and cancel. So anything that is the same on both sides of the arrow can be canceled out. So this 6 electrons and this 6 electrons, those are going to cancel. The 3H2O is going to cancel out 3H2O, leaving 4 behind. The H pluses, all 9 are going to go here, which leaves 5 here. And there's nothing else that's going to cancel. So my final task is just to combine those 2 reactions together. So here is my final overall balanced redox reaction in acidic conditions. It would also be the same in neutral conditions as well. But if this was basic conditions, we've got one more step. So I'm going to continue from this reaction. We've already balanced it. And I'm going to do one more step because this is basic conditions. So I've got that same reaction that we just balanced, and I'm doing this one more step. Now in basic conditions, any H plus in my reaction is going to get neutralized. So I'm going to put 5 OH minuses to neutralize those 5 H pluses. Now to keep this reaction balanced, I'm going to need to add 5 OHs on the other side as well. So 5 OH minus and 5 H pluses are going to give me 5 H2Os. So now I have more water that I can cancel out. So all 4 of the water molecules on the product side are going to cancel, leaving behind 1 on the reactant side. So now I'm just going to rewrite my final equation. So I've got that 1 water, and now I have 5 OH minus on my product side of my reaction. So for the next few problems, I want you to practice balancing using this half reaction method for these redox reactions. Label each half reaction as oxidation or reduction. So you can pause the video here and then spend some time working through these problems. And then I'll just put the balanced oxidation reaction, the balanced reduction reaction, and the final answer so that you can check your work. So what does it mean for a substance to be oxidized? Explain why a substance which reacts with oxygen gas is always going to be oxidized. So oxidation gas, or rather oxygen gas, has an oxidation state of 0. If it reacts and forms any compound, the oxidation state will no longer be 0, it will be -2. So that means that we're having oxidation occurring here. So O2 is going to always be something that causes oxidation in other compounds. If an element is a reactant or a product, the reaction must be a redox reaction. Why is this true? So any pure element will have an oxidation state of 0. So if it reacts and forms any compound, the oxidation state is no longer going to be 0. So those electrons must be transferred, which is what happens in a redox reaction. Now the equation Ag plus Cu to form Cu plus 2 Ag has equal number of atoms on both sides, but it's not balanced. And that's got to do with the amount of electrons. So for Ag plus to become Ag, it's going to need to gain 1 electron. And for Cu to become Cu plus 2, it's going to need to lose 2 electrons. So even though this is atom balanced, it's not electron balanced. So your reflection question, why do redox reactions have to be both atom balanced and electron balanced? So think about how one reaction needs to produce electrons and one reaction needs to consume the electrons. So a few reminders here. You should complete topic 4.9 topic questions and progress check questions. Lab 5 gravimetric analysis is going to be due on the 13th. So that is available for you in Brightspace to submit. Lab 6 is acidity of beverages. The background questions for that are due on the 16th. I gave you that lab packet last class. Same thing with my Lab 7 percent H2O2 by redox titration. I gave you that packet last class, and those background questions are going to be due on the 18th. Your mastery check for this unit is going to be on the 20th.